All right, today I would like to share the layout for wires. Maybe many of you will think, why the wires are so important? They are not any kind of devices, right? What kind of role they can play later, I will explain in such a good detail. This is some kind of cross-sectional view of the wires. As I mentioned, only the metal one can can touch the other layers through the so-called contacts. And above it, we call all those vias. And from this plot, you need to know that there isn't any via can connect metal 3 to metal 1. No. So how can you connect it? Or how can you connect metal 3 to polygate? Okay, you need some steps, some intermediate layers. For example, metal 3 via to metal 2 via to metal 1, and finally contact to touch polygate. This is what you need to do by yourself. If you have such kind of full custom design, you need to finish all those by yourself or through the help of your layout engineers. Allow me to show you some kind of anatomy for such kind of routing. Yeah, this is some kind of top view. Top view means the layout you do, right? In the two-dimensional way. But keep this in mind, nothing is 2D. Everything is 3D for our chips. So if you do such kind of layout, this is for layout view, but for schematic, actually, it only means 3 lines, right? However, actually, what TSMC or UMC help you manufacture actually look like this. 3-dimensional lines, okay? It is 3-dimensional, it is not flat, it is not any kind of 2-dimensional ones. Then we can go further. That is for metal 1, and then we would like to have metal 2. Yeah, you do such kind of layout. Similarly, this is the analogy for schematic, all right? But actually, metal 2 will be fabricated above metal 1. But how to connect them? We need the help of vias, right? So, for example, this metal 2 needs to connect to that metal 1, then we need such kind of via here, all right? But sorry for that, because this part was not drawn by myself. I just got help from the other professors. So what's going on here? Actually, the size of the via should be much smaller than this. Okay, as I told you, for example, this is the top layer and that is the bottom layer, right? So for such kind of overlap area, your via or contact should be smaller than the overall overlap area. That is what I mentioned. Maybe in chapter 2 or chapter 3. Okay, anyway, all right. So this is not to scale. 这个不是按照一般的尺寸来画。一般来讲，metal 1跟 metal 2，它中间或任何两层中间的那个 contact 或是 V 它的 size 一定要比上下层还要小。这我当初就有跟各位讲到过了。Okay, that's it. So, if you need, for example, if you would like to connect this one to another metal 3, then you still need the help of another via between metal 3 and metal 2, blah, 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 all of them. So hopefully you get correct understanding or feeling at least about such kind of 3-dimensional wires. Not only for wires, for everything. Everything on chip actually is 3-dimensional in such kind of overall structure. Okay, and what is the properties for different wires on chip? we have quite many wires. For example, except or in addition to metal knives, we can apply polysilicon for very short knife. Got it? Maybe even for N-diffusion or P-diffusion. But anyway, I don't think in any case, under any circumstances, you can apply diffusion area for connection. Yeah, that is a stupid idea, so forget about it. However, at least polysilicon can be used for very, very short knife, all right, to ease your connection, to make the connection or the wiring easier to handle by yourself. But keep this in mind, polysilicon is only good for short wiring. For long wiring, actually, we need to apply metal knives. Why? Because the resistance for such kind of metal knife actually is much smaller than poly one. All right? And then allow me to remind you again, I think we talked electron migration or metal migration in chapter 4. All right, but here again, I would like to emphasize for such kind of wires, you need to, especially for metal wires, you need to pay much attention for the width of the wires. Actually, you need to know the peak current. Okay, this is what I need to emphasize again. For each wire, you need to pay attention to the peak current the wire would like to carry. And after that, you need to set the width for the wire. Usually, for each milliampere, you need 1 micron. That is the easiest way. But according to your simulation, that is the, for example, this is the current consumption. Okay, the consumption current looks like this. Then don't pay attention to the average one. No. For metal migration or electron migration, you need to pay attention to the peak values. So after you get the peak value here, for example, it is 5 milliamperes. So what does it mean? To play safe, the width of the metal knife should be 5 micron. Okay, that is what I recommend. That's it. But if you would like to pay attention to all the wires, how many wires on chip you have? Oh, sorry for that. For big chip, I guess instead of millions of wires, I think it should be more than billions. 好几十亿,好几百亿. Okay, so can you pay attention to all of them? No. So only pay good enough attention to important wires. For example, the wire to be connected to power MOSFETs. Or for RF circuit, all those wires, for example, for LNA, blah blah blah. I guess they need to carry a lot of current. So just pay attention, good enough attention to wires carrying large currents. I guess good enough. Okay, and then again, pay attention to the peak value instead of average value of the wire. Then you can make the final decision how wide the metal knife should be. 我再次跟各位强调哈，我们为了对抗这种 electron migration， 那么你们需要注意的是那一些负荷比较重的，不可能每一条线啊，小可怕小无聊哈。你就来找那个负载比较重、电流比较高的那个金属线，然后呢要去看它的那个峰值电流 peak value， 不是平均电流啊，峰值电流多少，你大概金属线的宽度大概就是多少了。Okay. Anyway, if you don't follow my recommendation, then something may go wrong according to electron migration. Yeah, if the current, I'm talking about the DC instead of AC. Sorry for that. Okay. If the DC current becomes too much, then the electrons in the current will collide with the lattice of the metal 9, the crystal of the metal 9. So after collision, days of collision, months of collision, finally some of the atoms will be rushed out. All right? Then the weak point, will be pushed away faster and faster. Finally, it will be broken. That's it. That's the definition for metal migration. So what you can do? It's some kind of silly question, right? What you can do? The easiest way is to make it wider. Then the time for failure. Okay, yeah, time to failure or something, yeah, or time before failure. Okay, anyhow, all right, or be much longer than before. That's it. Good enough. Nobody will expect the chip to be functional for infinite time. No. For iPhones, for such kind of mobile phones, usually I guess maybe 2 to 3 years should be more than good enough, because the vendors just like Apple, Samsung, or Xiaomi anyway, I guess they hope the customers to buy new phones, yeah, for each new generation. And how long between generations? I guess less than 1 year. So if the mobile phone can only function for 1 year, then good enough. They will force the customers to buy new ones, and the companies can make a lot of money. Okay, that is good for them, but not good for users, even very bad for our environment. However, don't expect your phones can operate for 10 years, 20 years. It doesn't make any sense, because the overall environment should be changed substantially. So if right now you use some, how can I say, some smartphone fabricated more than 10 years ago, I don't think it can help you to run any kind of good programs or ad. Forget about it. You need to update not only your software but your hardware, right? So anyhow, yeah. Only if the metal 9 is wide enough to run, for the chip to run a few years, good enough, yeah. And this is some kind of solid proof for you. Maybe you will be curious, is it possible to have such kind of electron migration? Yes, please have a look at such kind of microphoto. You will see the metal 9 here is broken. All right, pay attention to this. I am not kidding. No, I'm serious. It happens if the metal 9 is too narrow to carry large current, then you need to face the consequence. Metal migration or electron migration. All right. So this is something for your reference. Anyhow, how long such kind of metal 9 can operate until broken? It depends on the material. So, for example, copper is better than aluminum. That's it. Yeah. Anyway, if you would like to know the exact value, as I mentioned, for 1 milliampere, how wide your aluminum 9 or copper 9 should be. For the exact value, you had better go back to read your technology files, then you will know the details. But for me, my very rough recommendation is again 1 milliamperes means 1 micron for your metal 9. I guess, roughly speaking, this should be good enough. Then let's have some kind of go back to the future. Yeah, to see what happened in the history. From the very beginning, this is the first chip, the first integrated circuit, the so-called IC. That is the first IC humankind ever made. In 1958, I think I told you such kind of inspiring story already. In that era, how to connect the devices? Totally, they are, to my memory, three transistors. And how to connect all those transistors? They use gold nine instead of the metal is gold instead of aluminum or copper. Anyhow, that is in the past. So according to the size, actually the metal nine actually is quite, other country, sorry, the device itself, the transistor actually is quite comparable to the metal nines. Or you can see the transistor here actually they are much larger in size than the gold nine, the metal nines, right? However, if you have a look at the 0.25 micron CMOS process from Motorola in 1996, totally, they have 5 metals. And where is the transistor here? So compared to the real size, metal nines right now. They dominate the size. It means according to the scale, they are much larger in scale than the main device transistor. But it is already how long years ago? Now it's 2021, right? Wow, almost 2 to 3 decades ago. So let's go back a little bit. So you can see for 19 nanometer, it's almost 20 years ago, 19 years ago, so about 2 decades ago, TSMC announced such kind of 90 nanometer process. You can see totally it has 9 metals, right? And where is the main device transistor? Here. You can see here is your transistor, your main device, but according to the size, metal nines dominates, right? It means in size, metal nines are much larger than your main device transistor. This is the reason why I always told you, I always warned you, the operation of our IC actually is quite, how can I say, is quite shallow. It is not deep. It is, according to my definition, it's only skin deep. Skin deep, right? Why? Because this is the surface of your substrate. Yeah, in theory. Yeah, that is the surface of the wafer, right? And we try to diffuse into the surface of the wafer or substrate to make your N plus or P plus region, right? For such kind of, sorry. For such kind of transistor, right? So you have, sorry for that. Yeah, your source region, your drain region, and above it, the gate, above the surface. But even above the surface is the metal 1, metal 2, all the way to metal 6. So all of them will carry the current to go through the source to the drain and backward to the metal 9. So according to such kind of three-dimensional structure, you can see the main device, I mean the transistor, actually is around the surface of your substrate. All the current flowing through the device, the main device transistor, actually only getting the so-called skin depth of the chip. Okay, so what's the impact? Current crowding. The current flowing through all those metal knives actually will be crowded around the surface of the substrate or around the surface of your wafer, of your chip. You need to pay very, very much attention to that. The current crowding will have some kind of impact for maybe the delay, the parasitic resistance, or even they will seriously limit the highest operation frequency the circuit can run. All right. According again, the skin depth of the current flowing through your circuit, your main device transistor. 我再次跟各位强调哈，总而言之一句啊，从最开始的这个 IC 哈，你的电晶体上面可能有3颗电晶体，据我印象手机，然后打了一些金属黄金线了。哦，那你可以发现哦，你的那个电晶体那时候的电晶体，它的 size 比金属线要大太多了。可是在1996年的时候，哈、各位看一下，点25迈的，哎呦，你敢看一轮中5盏啊，有5层的金属。那我们的电晶体大概是落位在这个地方，所以各位可以发现哈、在大小在体积上面，其实金属线已经远远超过你的本尊啊，你最重要的元件就是电晶体嘛，对不？各位再看一下，哎呦，在2002年，距今已经差不多20年前了，今年已经2021了。各位可以发现，那时候台积电的90奈米，它的纵剖面积长成这副德性，你总共有9层金属，但是，你的主角电晶体在哪里？电晶体嘛是你家，在非常肤浅。为什么我讲它肤浅？非常肤浅的地方，因为它就集中在那个晶圆或是那个基底啊 substrate 的那个表面附近嘛。哦，所以这个冲击是什么？你有这么多层的厚重金属，它们所承揽的电流都要涌入这个肤浅的那个表面，去让你的电晶体工作，所以它会有所谓的涌流效应啊。涌是拥挤的涌啦，current crowding 呀。那因为这种涌流效应呢，它就会造成怎么讲？会有比较大的那个电阻会跑出来啦。好，那通常来讲，它的冲击就是说，在高速运作的时候，你的频率就会受到相当严重的限制，所以领导来做布局哈，这种概念一定要有哈。再次跟各位强调，那个我们的主角电晶体只存在那个肤浅的表面附近 ，OK 所以要非常小心那个所谓的那个涌流效应啦Okay, allow me to show you the cross-sectional view of the very old but quite mature process, 0.35 micron. Even till now, I guess it is still survived. Okay, it is still survives, or actually it's still very good for the market, especially for modem. Yeah, for the mobile phone modems, I mean transmitter and receivers, they need to tolerate higher voltage to generate higher power and to get some kind of longer transmission distance, right? Nothing is free. How can you tolerate such kind of high voltage, high power application? Usually you need to use such kind of very mature process. And maybe this is also the reason why Qualcomm was defeated by MediaTek in last year, because Qualcomm focused its chip fabrication very much on Samsung. But Samsung had some kind of problem about the 5 nanometer process fabrication. Also, the yield is not good. And the other issue is, that is for the core chip. And how about for the modem chips? Maybe they ask help from Samsung to fabricate the chip in Texas, to my memory, but it went wrong for some kind of big snowing, and many of the foundries there were forced to shut down. Even till now, maybe they don't get back 100% of the production. That is really harmful for Qualcomm or the other companies. Depends on the fabs in Texas. Anyhow, for MediaTek, actually the major base for the chip fabrication actually in Taiwan, from TSMC or from UMC. Even they get chips from UMC, especially for such kind of mature processes, is still very important. Okay, since 0.35 micron is still very important, you guys had better to get some kind of good feeling, good understanding about such kind of mature process. Now you can see this is the active area means the area for your MOSFET, your gate, source, drain, and body. Okay, and above it we have poly 1. That is for gate. That is for gate usually. And then between the channel and the polygate, actually, there is a very thin gate oxide, silicon dioxide. And above it, we have poly 2. For what? Poly 1 and poly 2 all together to compose the horizontal parallel plate capacitor. Poly 1 跟 poly 2 是要组成那个水平面电容的and above poly 2 we have metal 1, above metal 1 we have metal 2, and then metal 3, metal 4, blah blah blah, all the way. Okay, and above it we have the chip fully covered by glass, okay, for protection, to insulate the whole chip from the air, because in the air we have oxygen, and the oxygen will make all those metal layers to get some kind of oxidation very easily, right? It's really harmful for such kind of metal oxidation, so we need to insulate the whole chip from the air. But you need to have some kind of opening, because for your pads, I/O pads, probing pads, they cannot be insulated by the glass. No. They need to be connected to the outside world. So we need to have such kind of opening here. Okay, we call it passivation window. Passivation window. Okay. Anyway, I would like to explain how, especially for your metal knives, how close they can have. Okay, first of all, for the thickness, you will see here maybe 0.6 micron in thickness. All right, and what is the spacing between the metal 1 and the metal 2? You can see almost 1 micron. Okay, and again, for how about metal 2, the same, maybe 0.6 micron in thickness, and for spacing it is 1 micron, blah blah blah. Have a detailed look by yourself. For such kind of thickness and spacing for metal knives, you can see TSMC or UMC, they dare not to scale them down very fast. Why? You can see if they scale down the metal knife thickness, then it means what? It means the resistivity will be increased, right? The thinner, the worse. 越薄的金属线电阻越高。And then, how about the spacing? How about the spacing between metal layers? Actually, it is 1 micron, right? It means they are far away. Why? Because we would like to reduce the parasitic capacitance between those two knives. Again, TSMC or UMC, they will not scale it down very soon. If they reduce the spacing between metal knives, then the parasitic capacitance will be increased substantially. It is really harmful again for high frequency operation, right? That's it. That's it. So for process evolution, the fabrication company tried their very best to reduce the width of the metal knife, the spacing among metal knives at the same layer. Okay, that's it. It means process evolution happens almost for horizontal issues, horizontal parameters. So the width of the metal knife actually is horizontal, right? The spacing here, I mean for the same layer, for the metal knife on the same layer, actually they are also horizontal spacing. And how about the vertical spacing between different metal layers? Sorry for that. No much evolution happens vertically. Evolution usually happens horizontally. Okay, please keep this in mind. That is really important for all the processes. And also that is some kind of limitation by nature. If you reduce again the thickness vertically, sorry for that, the resistance will increase for metal knife. If you reduce the spacing between layers, between the above and the below layers, then the parasitic capacitance will be increased. It is really harmful for high frequency operation. Please keep this in mind. So in brief, the overall accuracy is along horizontal direction. The accuracy is much higher than vertical direction. Got it? That is the secret for TSMC and UMC. Okay, it means what? Your layout had better depends on horizontal accuracy instead of vertical accuracy, because vertical accuracy is much poorer than horizontal accuracy. Okay, that is the secret. So try your very best to make your circuit, your layout depends on horizontal parameters much more than vertical parameters。好，我这跟您讲一个最重要的重点就是讲，咱的制程微缩都是发生在水平的这个方向水平的宽度要变窄，水平的间距要变小，但是我刚刚跟各位解释过了，垂直的厚度不能变小，不然你的那个阻抗。金属性的阻抗会变高，然后垂直的间距不能变小，为什么？不能变得太快不能小太快，为什么呢？因为不同金属层中间你的那个杂声电容会变高所以总而言之一句话，水平精度因为不断的微缩，所以它的精确度会远超过垂直方向的精度，各位一定要记清楚。所以你的电路你的布局如果比较重压在比较注重在你的水平精度上，你做出来就会比较好。如果你的电路需要依靠垂直精度你代志就大条5大条这大条伊的精度会出问题所以恁大家一定要给记录清楚，好不好？ Please keep this in mind. Keep what in mind. Anyhow, the horizontal accuracy is much higher, much better than vertical accuracy. Please keep this in mind. Keep this in mind to make sure your circuit layout depends on horizontal accuracy instead of vertical accuracy. Okay, that is a very good proof for you to compare this old process with the other also very old process. However, there are two generations in between. From 0.35, the next actually is the so-called 0.25 micron. Actually, that is 0.24. I have no idea why humankind called 0.24 micron, 0.25 micron. I have no idea. Don't ask me, okay? And after that, after 0.25 micron, humankind touch 0.80 micron. If you compare the thickness of the metal nut, you can see, about the same, right? Even though the difference between those two processes are 2. They are 2 generations in difference, but you can see for 0.35, the thickness is 0.6. And now it is only 0.53 micron. Got it? And how about the spacing between between 2 layers? You can see 0.85. But in 0.35 micron process, it is 1 micron, right? So again, it is a solid proof for you guys. The evolution along vertical axis is much slower compared to horizontal one. So again, you had better make your circuit, your layout depends on horizontal parameters instead of vertical parameters. Okay, then how to model the wires for good simulation? You need something like this, but it's too painful, too troublesome. You need to extract not only the resistance, capacitance, but also the inductance. That's too much. So my recommendation is forget about L, unless this layout is for very high frequency operation. For example, gigahertz. Otherwise, forget about it. Forget about what? Forget about the inductance. You only need to extract usually R and C. Good enough. Okay, for your post simulation, don't touch L. That is too much. Alright? Good enough for almost all the circuit and operation. I mean R and C parasitics. Good enough. Yeah. Anyhow, what is the impact of such kind of interconnect? I mean the metal knives. How much will be the parasitics? Okay, let's go further. We have capacitive, resistive, and inductive, but usually I told you already, we don't touch the inductive parasitic. Then this is some kind of nature of interconnects from Intel. You can see from Intel, this is the length of the metal nut, and for the vertical axis, the number of nodes those knives connected to. Okay, you can see the tendency look like this. It means the longer, the less nodes to be connected. On the contrary, the shorter, the more nodes to be connected. That's it. But why? Okay, a very simple explanation is for such kind of long wire, actually they are used to connect among blocks. For your chip, you have many kind of sub-blocks, right? And how to connect all those blocks? You need long metal knives, right? So for such kind of long distance connection, usually it is composed of the top metal. Yeah, for example, metal 6 for your 0.18 micron process. All right. For such kind of thick metal, you need to go up from your device. Contact metal 1 via metal 2 via metal 3 all the way to metal 6. Then you need to go down reversely. Oh, it's a painful process. So in practice, we don't use such kind of top metal to connect many nodes. No, very few nodes. But for a long distance, got it? For very short distance, usually we apply metal 1 if you have a look at this again, okay, the device contact the metal one, then contact the other device, contact the other device, blah blah blah. So usually for such kind of metal one connection, it is much easier, right? So usually it is for local connection, local interconnect, and usually it can help you to connect a lot of layers locally in a short distance, I mean. Okay, that is the truth. Not only for Intel, but for almost all the companies on Earth. Then let's go for the parasitic capacitance of the metal nice. This is what I would like to share with you. That is the previous stage and the next stage. In between, we need to connect the output of the first stage to the input of the next stage. And which limits the operation frequency? The parasitic. They will mention maybe including parasitic capacitance and also parasitic capacitance. In this subsection, we would like to focus on parasitic capacitance. Got it? So you can see overall how much capacitance, how much parasitic capacitance you need to face for such kind of interstage operation between the first stage to the next stage, right? Anyway, anyhow, you can see not only the input capacitance of the next stage, not only the output capacitance of the first stage, but also the capacitance of the wire to connect them. All of them needs to be counted. Got it? So if you would like to operate this circuit at the highest frequency, you need to reduce all the parasitics. Again, you not only need to reduce the parasitic output capacitance here, to reduce the input capacitance there, but also you need to reduce the capacitance of your wires, your interconnections. Okay, that's it. Maybe you'll be curious for such kind of wire. It is very narrow, very small. I mean, in size, the wire is supposed to be much smaller than the output stage and the input stage, right? So you may be curious how much capacitance it can get. All right, allow me to show you this for each wire. All right, for example, this is the wire, and below it you have substrate of the other layer. I don't care, right? I would like to say, even though you don't have the other layers below it, then below the wire, especially the metal one, for example, you have substrate, and then there will be some kind of parasitic capacitance between the wire and the substrate. According to the definition for the so-called parallel plate capacitance, just look like this. If they are two plates, or nice as you like, okay, they are conductive, and in between you have some kind of insulator. For the insulator, it has such kind of epsilon, right? The dielectric constant. Then you will see the overall capacitance equals the epsilon, the overlap area by the distance between them. Okay? Never mind what kind of place you have for the top one or for the bottom one. I don't care. Only if the top and bottom plates, they are conductive, and in between you have insulator. Then by definition, from fundamental physics, you have capacitance. Okay, so let's have a detailed look of such kind of very simple structure. You have metal 1,9. Below it, you have substrate. Most are conductive, right? And in between, you have what? silicon dioxide. Bingo! It means the metal 9 and the subject fit such kind of requirement for parallel plate capacitance. Right? That's it. So you can calculate it. The ideal capacitance. Ideal. Pay attention to this word ideal. It means what? In practice, not only. Okay? In ideal, you have only such kind of parallel plate capacitance, and you can see in practice maybe not too much. However, let's go further. Yeah. Before, however, let's finish the parallel plate capacitance. But what I warn you is parallel plate capacitance is not the only one. We have the other. Later I will show you. Fringing field, fringing effect, 弯曲的电力线。那我现在要跟各位讲，就是说，从基本物理来看，你至少，只要你有上板有下板，上下两板可以导电，我无你插你外口导电啊，即你会导电就好啊。因中间有迄绝缘层，这绝缘层有介电系数啊，你就代志大条啊，偌大条，这大条，你就有啥物？你就杂散电容电容那给你搞过来，电容的公式就是你的介电系数乘上你的面积除以你的距离就是安尼咩？你讲同简单的讲这条若是 metal 1伊下骹通无嘛有迄基底啊，冇 subject 伊中两个人中有二氧化硒代志大条，二氧化硒伊的介电系数就3.9嘛，除非你有再掺杂其他东西嘛，所以完全符合那个平板电容的定义啊！你有上板金属，下板是那个基体，然后中间有绝缘层二氧化硒，有介电系数你都要去算这种理论上平板电容所造成的杂散成分。不过我都要给你千交代万交代平板电容不是唯一的杂散成分，我们有更可怕的就是边缘电场所造成 fringing effect 所造成的效果，还能带它讲。Okay, let's go further before we touch the second parasitic capacitance. This is the first. In idea, you have only such kind of parallel plate capacitance. So in between, we have silicon dioxide, right? And what is the permittivity? The dielectric capacitance actually 3.9. But you can doubt the other metal atoms to change it. If you reduce it, congratulations, the parasitic capacitance will be reduced also. But if you increase it, then the parasitic will be also increased. It is really bad for wires, but keep this in mind. It will be very good for real capacitor, right? So anyway, anyhow, for wires, we try to reduce the permittivity, okay? But for capacitors, you need to try your very best to increase it. So the large or the larger, the better, or the smaller, the better. It depends on your application. For pure wires to connect the devices, we hope the less the less the better. Right? But if you would like to compose, to construct your real capacitor, then the larger the better. Got it? 咱给强调一下讲，这种介电系数伊是较大颗较小颗真歹讲。你若要做电线，要做连接线，那当然啦，杂散电容越小越好啊，所以介电系数越小越好。不过，如果你真的要拿来做电容的话，介电系数越大越好所以水能载舟，亦能覆舟。各位要讲清楚，水能覆舟，亦能载舟。如果你的介电系数大那对连接线来讲不好，它会覆舟。可是你如果把这种东西拿来做电容，你就不好洗啊，它的那个它的电容值就会变大你就很爽啊，因为同样的电容值。你只需要比较小的面积当然越大越好。所以天底下的事情没有绝对的对或错 ，OK？ 有些时候大比较好，有些时候小比较好，没有绝对的好坏，没有绝对的对错 ，OK？Let's go further. The second effect for parasitic capacitance, we call it fringing capacitance, OK？ at the boundary 边缘的 Yeah. So please keep this in mind. In the past, humankind only focused on this. That is in theory. Parallel plate capacitance. But nowadays, fringing fields become more important than before. The more curvature here, the more energy you can store. Alright. So it is really harmful. It is really harmful for wiring, for interconnect. But this impact again, if you would like to design real capacitor, then fringing field can help you a lot. The more curvature, the better for capacitor, for real capacitor. However, the more fringing field for interconnect, for wiring, the worse. Got it? 好，我要讲解哈，咱古早哈，敢若重视理论上的这个平板电容啦。事实上，边缘的这个部分哦，它的电力线扭曲的越厉害，能够储存越多的能量所以你代志大条。如果你只是拿来当做连接线的话，那么它越扭曲你越倒霉。但反过来想，水能覆舟，亦能载舟。如果你要拿边缘电场这种扭曲的边缘电场来建构你的电容的话，你毛死了，因为它可以大幅增加你的电容值，何乐而不为？这个东西就是 MOM，OK，MOM，它就希望能够大幅的去利用这种 fringing field 来提升单位面积的电容值。OK，for fringing field, we are afraid of it very, very much for wires, but we like it very, very much for capacitor. That is the major idea for MOM, right? Metal oxide metal. It is really, really good for such kind of MOM capacitor. In brief, MOM capacitor try to take advantages of such kind of fringing field as much as possible. Got it? Nothing is perfect. Sometimes it is bad. However, for the other sometimes it is good, right? Fringing field is really harmful for wires, for interconnects, but it is quite beneficial for capacitor. Keep this in mind. You need to know what you are doing. You need to know everything. Go to the bottom to get all the detail. Then look into the future. You will make the best decision for your circuit, for your layout, to achieve the best performance for your design. Bingo! Anyway, that is only the idea. If you would like to analyze how much fringing field such kind of metal line has, it's really troublesome. In theory, it is something like Mission Impossible. So years ago, somebody figured out such kind of fringing field can be approximated by this cylinder line, 圆柱状的 Okay, so for the cross section, it is a circle, right? Plus the parallel plate capacitor in theory. That's it. So they try to approximate the fringing field by this regular structure. And for this regular structure, it can be calculated. Much easier to calculate than this one. Okay, that's it. Again, I am your analog IC design or layout teacher. I am not such kind of EMI teacher for you. Okay, for EM wave, I almost forgot everything from my teacher. Sorry for that. Sorry for my EM wave teachers. I forgot almost everything. If you are curious why for such kind of structure you can calculate You can calculate the capacitance in this way. Don't ask me. Don't ask me. That is not my responsibility. That is your own problem or your EMOF professor's problem, not me. All right? I'm not interested at all. I believe in the paper, and then when necessary, you can or me can apply this to calculate the fringe field. However, I'm not interested at all, so I don't calculate it. Anyway, for accurate simulation, who calculates this for me? Our EDA tools. Through the help of the models in the technology files. And it means TSMC, UMC, along with the EDA companies, will help you to realize everything, including this, for you. Okay? I'm not curious. I'm not any kind of curious cat. So I don't need to I don't need to risk my life. OK？ 我不是好奇的猫哈，所以我的生命不会有危险哈。不论如何啦哈，你相信也好，不相信也好，为什么你可以拿这个东西来逼近那个边缘店长？卖甲问哈，我不是你电子科的老师哈，你若有兴趣，你等于家己去读你电子学，不你去问电子科的老师，不要烦我哈。我相信这个公式是对的。然后我相信台积电、联电跟 EDA 这些公司都帮各位把这些好的公式甚至比这个还复杂的东西都把它弄进去了，这些那卖差别他们还有实验呢，所以可以推出更精准的东西出来。Anyway, anyhow, I would like to share this with you: the fringing field versus parallel plate. For the metal line, the simplest, the metal line and the substrate. How much total capacitance you have? Total means what? In theory, you have such kind of parallel plate capacitance along with your fringing field. So that is for the total. Okay? And it means what? The difference, for example, here. Okay? This is for what? Parallel plate capacitance. In theory, right? And that portion is for what? Fringing field. So in the past, when the width of the metal line is large, is wide, parallel plate capacitance dominates. On the contrary, when the width becomes narrower and narrower, you can see here, this portion, okay, this portion is for parallel plate, and that big portion dominates by fringing field. So it is really harmful again if you have very narrow wires in this region. Fringing field will dominate the parasitic capacitance. It means what? The total capacitance is much larger than your imagination, because your imagination usually here, you guys only cover the ideal capacitance according to parallel plate structure, right? And for process evolution, as you can see, the width of the metal line becomes smaller and smaller than before. Then it means what? Fringing field becomes much more important than parallel plate capacitance. Got it? Got it? You must be very careful. Okay, it is really harmful for wires, but it is really good for capacitor. Anyway, the ugly truth is the real situation is much more complicated than this one. That's too simplified. Actually, we have a lot of layers, we have a lot of wires, so you need to pay attention. Not only the ideal value here, see? The ideal parallel plate, the fringing field, but also the fringing field, because here we only focus on the metal 1 and the substrate, right? Anyway, we have not only metal 1, we have metal 2. And even for the same metal one, we have this metal 9, we have that metal 9. So, wow. It means what? You need to pay attention to all of them. All kind of parasitic capacitance. You need to pay attention to. That is too complicated for our brains. We are humankind. We are not machines. We are not AIs, right? So what we can do? Through the help of your EDA tools. But you are the one to make such kind of layout by yourself for full custom design, right? So try to simplify your wires, your routings, your interconnects as neat as possible to reduce all the parasitics. That's it. That is my recommendation. OK， 我咧甲你讲就是讲吼，你看头前即个 model， 咱敢若一个 metal 1加迄 subject， 你就用甲喙手就要拍甲啦吼，实在是有够恐怖的。实际上，你除了 metal 1， 你还有 metal 2啊，同样的 metal 1，你有这条线，你有那条线，所以啊，它们中间的关系，它们中间的那个电容实在是复杂到不行了。哦，我没有叫你自己去计算这个，没有 ，EDA tool 我会帮忙，但你要尽到你的责任。也就是说，你尽量简化你的这些拉线，把它画的越精简越好 ，as neat as possible. Then we can reduce the parasitic capacitance between them, among them, very much. Okay, so as I mentioned moments ago, for each 9, you have something below you, you have something above you. Right, you need to consider all of them. The parallel plate capacitance and the fringing field, blah, 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 all of them. So if you would like, you can do such kind of simulation. Instead of calculation for us is totally impossible. That is too complicated and time wasting. So it depends on our EDA tools very much. And again, you can see we have parallel plate capacitance, we have interwire, we have fringing field, all of them. So totally, you have such kind of, again, smiling curve, right? For interconnect, you had better reach the minimum. The minimum capacitance means the maximum perforation frequency you can achieve for your layout, for your circuit. That's it. All right. Okay, so at this, why it is smiling? Because when it is wide, as I explained already, parallel plate capacitance dominates. When it becomes too narrow, fringing field dominates. So in between, you can reach the value, the minimum. Okay, if you would like to know what is the absolute value for the value, it's hard to say. It's hard to say. Here you can see it is normalized. Everything is normalized. The width is 1 micron. The thickness is 1 micron. The gap, the spacing is 1 micron. It is not real, right? Everything is normalized to 1 micron. So if you are interested, you need to denormalize it by yourself according to your technology file. So for example, if everything is 1 micron, then you can guess what is the minimum. Yeah, about 1.5 micron, right? But according to your process, I think everything is less than 1 micron, right? The thickness, the width, the spacing, blah, blah, blah. So. In practice, the absolute value to achieve the minimum capacitance is less than 1.5 micron. My first recommendation for you is again 1 micron. If you have no idea, then 1 micron metal 9 will be a good guess for you from the very beginning. Okay, that's it. If you would like to go to the bottom, okay, you need to, the easiest way is to do the layout and extract the parasitic by yourself. then you can fine-tune the width, blah, 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 all of them to achieve the minimum capacitance. If not, then 1 micron or something a little bit less than 1 micron, I think should be good enough for most of the nights. Okay, but for accurate simulation, especially for RF circuit, if you would like to connect the device in your LNA, I think you had better try your very best to simulate everything accurately to make the final decision how wide the metal knife should be. Okay, let's go further. Yeah, anyway, as I mentioned, when the width of the metal knife over the thickness of the metal knife, okay, H, where is H? Where is H? Here, yeah. See? Here? The width of the metal knife over the thickness less than 1.5, fringing field dominates this region. Okay? As you can see, I emphasize again and again, humankind still not reduce the thickness of the metal knife too much, even according to process evolution, right? We try our very best to reduce width instead of the thickness. So it means what? For all the new processes you have nowadays, actually is already much less than 1.5 for such kind of W over H. Pay attention to your fringing field. All right, it is again harmful for wires, for interconnects, but it is really good for capacitance. Congratulations. If it is much smaller, then you can see fringing field may be one order higher than your parallel plate. It is again very harmful for your high frequency operation, but it is good for your real capacitor. Okay, then I would like to share some of the parameters with you. This is from 0.25 micron CMOS process. For different layers, actually the figures, the numbers are not the same. Yeah, and anyway, it's only interesting. All right, I would only like to point out this. What is the unit? It's really, really small. Atom. The minus 18th power of 10. Wow, really small, right? That's it. Before, above atom, we have femto, right? Minus 15 power. And then pico. Pico, I think you already know. Minus 12 order, right? And then narrow, blah, blah, all the way. Yeah. And maybe this is the first time in your life to see such small unit. Atom. And which one is below it? Don't ask me. For minor 21st order of 10, if you are interested, Google online by yourself. Let's go further. So for our layout solutions, usually don't mix the wires of your analog circuit and the digital circuit. Don't mix them up. Otherwise, the noise of the digital wires will be coupled to your analog circuit, to your analog noise. It is really harmful for your analog circuit. By the way, you had better separate to keep them far away enough. And to make it even better, you can have some kind of shield. Usually we have guard ring for shielding. Okay, then let's go further. Yeah, again, this is some kind of three-dimensional view. I think I told you already. Yeah, usually we do layout for such kind of wires orthogonally. I mean, with horizontal line and vertical line. Okay, yeah, but if you can accept the wiring along diagonal axis, just like this, In practice, EDA tools can help you to reduce the layout area for the same wiring, okay, for the same interconnects. If you limit the EDA tools to have such kind of orthogonal layout, 正交型的水平跟垂直的这种拉线 orthogonal layout for wires, then you need some more area for the same connections. Okay? With diagonal wiring, again, EDA tools can help you reduce the required area. So it's up to you. Yeah. Especially if you have cell-based design. Why not? 如果你用数位的那个 cell-based 的那个设计的话，何乐而不为？就接受吧。让你的 EDA 有更高的弹性，那么它绕出来的面积就会变得比较小。